Welcome everybody to CS196 Lecture number 19. Today we are discussing the long-awaited, the much hyped AI and ML lecture. And so without further ado, we'll first talk about some course announcements. Obviously, we have our midterm tomorrow. I hope you've all been studying hard. We'll just get this out of the way. And obviously it's April Fool's. Yeah, I mean, I kind of had to, so it's better just to get it out of the way now than later. So I hope you all appreciated that, or maybe you didn't. Either way, April Fools, right? So, in more seriousness, let's talk a little bit about the objectives for today. Um, First, we're going to be discussing kind of the major differences or the major topics of what is AI, artificial intelligence, ML, machine learning, and DL, deep learning. Then we'll start to kind of dive deeper into the ML field, and we'll talk about unsupervised versus supervised learning. And then we'll also kind of dive more into the deep learning field, and we'll talk about the oh so popular neural networks and some of the applications of it, and that'll kind of quickly move us into the topics of the different subtopics, examples in ML, and resources. Yeah, and any resources that you may have in order to learn more about this stuff. Now, in full transparency, this is a pretty beefy lecture. Hopefully not in terms of the difficulty in the content, but definitely in terms of the quantity of the content. And so one thing that I want to reiterate that, I do say a lot of lectures, but I think upholds in this one especially is, you don't need to memorize all of this, of course, but what we're really looking to do is introduce you to these concepts and show you that these things exist. And, specifically, we'll kind of discuss this as why do we want to learn machine learning? Well, in the past, 30 years ago, which is actually relatively recently, ML was not that popular, believe it or not. I know nowadays it's crazy, and only because of recent advances and recent breakthroughs has ML become a tool that can be so widely applied to so many companies, to so many fields, and actually be useful in that way. And really, one thing that it is it's become a tool, right? And it's a tool that a lot of companies and especially a lot of developers, meaning you eventually, should really have in their tool belt and should have as a skill or at least have the knowledge of. And you don't need to spend maybe one of the thoughts or in order to keep up with ML, in order to know what you're doing, you have to do all this research and have all this background knowledge, and it's crazy math and crazy statistics to know what's going on. And I really don't necessarily think that's true. I think as we mentioned just a second ago, ML is a tool that a lot of people should have in their tool belt. And so really a basic understanding is more than enough to know when you need to use what. And realistically, when you're working somewhere, knowing what you need to use and maybe not necessarily how to do it yet is, perfectly acceptable, right? A huge part of working in computer science is learning as you go because you can't be expected to know every language. You can't be expected to know how to do everything. There's just, infinite things and infinite programs that can be written. And really, this is a part that I want to harp on a little bit, which is what I want you to take away from this is to know when to use what. And kind of two major parts of that is knowing what there is and then maybe knowing some of the applications, so what it does, right? And I could talk about machine learning and the subfields of machine learning for many, many, many lectures, and I wish I could. But unfortunately, we are restrained to only a single lecture. Maybe in the future it could be two. But again, really what I want to reiterate on is no matter what your focus is, whether you're interested in doing exclusively CS for good, whether you're interested in studying ML for the rest of your career, I really want this to be a time when you can learn about what there is and maybe learn about what they do at a high level. We're not going to get deep into the math. We're not going to get deep into the code. Though you will hopefully be exposed to a little bit of that in your homework. We're going to keep it relatively high level here. And so let's without further ado, kind of start talking about the actual content. And that is, what is the differences between artificial intelligence, machine learning, and deep learning? Well, we'll start with AI. AI refers to the practice of trying to emulate human behavior or emulate human intelligence using machines and using kind of code. And so there's kind of a big question here, which is, what really is that? Uh, Artificial intelligence is the science and engineering of making intelligent machines and especially intelligent computer programs, right? And this is a quote from, I think it was a meeting, a symposium of some sort, where they just kind of discussed like what is ML. Very famous researcher John McCarthy was kind of the lead of this. And one thing that we maybe need to define a little bit more specifically is, what is intelligence, right? We've said that machines and artificial intelligence is the act of having a computer do these things and having intelligence and emulating human intelligence. But what is this thing that we call intelligence? And there's probably no great answer, but one answer that we're going to use is the ability to achieve goals. And another thing that we can call goals here is tasks. And in fact, that's a term that we'll use a lot as we move forward, is the ability to solve a task, learn about a task, infer information in a task, and perform a task, right? When you're training ML, you train a model on a task, right? You want to learn about that task. And so really, what I want to harp on is intelligence, and artificial intelligence is the ability to achieve some task, to through the means of a computer program, is what we'll say. Now, obviously, tasks are incredibly broad, and so we have kind of the bubble of AI. And if we want to just talk about things that are AI but maybe not machine learning, if then statements and like basic functions are emulating human intelligence, right? In previous homeworks, if you want to treat a GET request and a POST request differently, you use an if statement, and that is emulating human intelligence and emulating human behavior. You, if someone came up to you and said that they wanted to do this thing, would treat those requests differently. Therefore, we can kind of call that artificial intelligence. Now, does that mean that artificial intelligence becomes this hugely broad category? Yeah, maybe. It's kind of a vague term to begin with, if we're being honest. But the general idea is, if your goal is to emulate human behavior, as we said, it probably fits somewhere under the umbrella of AI. Now, we'll get a little bit more specific, and maybe a little bit more specific to the things that people commonly think are actually AI, and we'll talk about machine learning. And machine learning is the practice, as we see here, is the practice of applying algorithms to data in order to learn, infer, or otherwise understand the data. Data. Now, really the two parts that I have underlined here are the most critical ones. Is first, the algorithms that we're going to use that are going to learn from this data somehow, and second, the data itself. Obviously, that's a kind of a critical piece. Is the whole idea of machine learning is you have some data set that you would like to learn from, infer, or you otherwise understand. And by applying these algorithms, we can get useful information out. And so we then have kind of the bubble of machine learning, and we have all sorts of things that fit under here. So we have your linear regression, your linear classification, we have things like random forest, we have things like k-means clustering, and of course, everyone's favorite, we have things like neural networks. And then finally, we'll talk about deep learning, which generally focuses on a specific subset of algorithms that have been found to work really well on complex problems with a lot of data. And so what do we call a complex problem? Well, let's first maybe... Oh yeah, sorry. We have our deep learning bubble here, and we have things like neural networks, CNNs, RNNs, transformers, which are different kind of flavors, varieties of neural networks, and then we have the whole topic of like backpropagation. And so, why do we actually need backpropagation, and what kind of separates machine learning and deep learning, the whole complex problem? How do we define that? Well, we'll look at maybe a more simple linear regression case, right? You have maybe two parameters here, your slope and your bias. And as we can see here, there's maybe a clear solution. There's an easily found, optimal point where your error is the least, and if you can get your slope and your bias to those points, then you have the best solution for that data set. And in fact, we have what we call a closed form solution for this, meaning if you have your data set here, which we call X, and you have your labels here, which we call Y, you can extract the correct answers just by solving this equation. And so, maybe that's surprising to you, maybe it isn't. Uh, but let's maybe draw a contrast with what we'll call a more complex problem. And so maybe this is what it looks like. And so, as we have different variables that we are changing, your slopes and your biases, your error changes rapidly and drastically. As you may be able to imagine, there's not a closed form solution to this. There's not a simple equation that we can solve for. But rather, we do this approach of picking a random spot and then moving to a slightly better spot and then doing that again until we're happy. And we'll really look at that in a lot more depth later in the lecture. But keep in mind, maybe how much more complex these problems may be. So machine learning, oopsies. I messed up the animations, feels bad. So let's talk a little bit more. I want to provide you with two more quotes that I saw in the ECE 449 or CS 448 class, which is titled Machine Learning, that really helped me a lot and really helped me understand it. And so these two quotes, the first one, machine learning uses statistical techniques to give computer systems the ability to learn with data without being explicitly programmed. Right? And really the key word there is without being explicitly programmed. If you were to try to hand code all of these rules to maybe identify a digit or say, is there a cat in this image, you would be tearing your hair out for years because it's an incredibly complex problem and almost, I would say, infinite edge cases, right? What if the cat is at a different angle and then it suddenly looks totally different, right? And another quote that we'll give is a computer program is said to learn from an experience if its performance at some task, as measured by some metric, improves. And there's three major things that I want you to take away from that second quote, which is you are learning from experiences at some task or for some task, and you measure your performance by some metric. And so let's break these down. Experiences, what is that? Well, that's the data set that we work with. The task is, well, the task. We're kind of using that terminology, and so we don't really need to rename it. And then the metrics is this thing that we're going to call the loss function, and we'll talk about that in a bit more as we continue. First, we're going to be starting to dive into machine learning here. And now that we maybe have the groundwork that machine learning is, doing better at some task with some data set, that machine learning is learning from data through some algorithm, we're going to be splitting it into kind of two separate topics here, unsupervised machine learning and supervised machine learning. And first, we'll look at unsupervised machine learning. And the distinction in this is that we don't know the right answer for the data, right? If we have pictures of cats, we don't know whether something is a picture of a cat or not. We can maybe in the future manually label those, in which case it becomes a supervised problem. But in this case, we don't know, and we just have that data set. Yet we still want to infer or mess with or otherwise learn from the data set in some way. And so, generally speaking, and this isn't maybe a perfect generalization, but we'll generalize nonetheless, is unsupervised methods fit under one of three categories: clustering, anomaly detection, and dimensionality reduction. And let's talk about each of these a little bit more specifically. First, clustering. So for clustering, we have some data set, and we want to know if we can cluster our data into groups in a kind of efficient and effective way. And so we'll talk about just a couple algorithms that are used for clustering. And the reason why we do this, once again, I want to remind you all, is because I want to expose you to these ideas. So if you ever are faced with a clustering problem, or you want to know if there are certain groups in your data, you can think, oh, Eustis talked about this, and CS196 I learned this, and I can use k-means clustering here. In k-means clustering, again, we're not going to get into the math. We're not not going to be talking about this for too long, but I just want to introduce these ideas to you. Is basically you pick 3 random points, and you slowly move these points more towards the average of the points that are labeled for them. So the green point here we can see is in kind of the center of these, and as the blue point moves closer, the average kind of location of all these green points becomes more over here. We see the green point move over there. Similarly with the blue point, it moves up towards its average location. And what we find here is that generally speaking, when you go for long enough, you start to find clusters. Now, is it perfect? No. And one maybe specific failure case is the initialization really matters. And so when we see in this second case, we can maybe clearly see 5 clusters here, and k-means kind of fails, right? We split into maybe not so great clusters. And so we'll talk about another one called expectation maximizing clustering, or EM clustering, which works similarly to k-means. There are some maybe significant differences. I'm not going to get into the math, but behind it. If you are interested, go back to the slides. There's a link here that discusses it. But basically what you're trying to do is, as the name suggests, maximize the expectation that a point is in a certain distribution. And it works in distributions instead of what we call these little clusters, right? So it's just like a little bit of a different approach. There's pros and cons. Again, if you ever are kind of working in this space, maybe look into the differences, which one your data may be better for. And then we have one called dbScan, which stands for Density-Based Spatial Clustering of Applications with Noise. Just call it dbScan. No one cares what the acronym stands for. This one's kind of a newer approach, and it's kind of fun. You pick a point, and you draw a little circle around it, and you keep drawing circles until you run out of points. And then you pick a new point and draw circles around that. And as we can see here, it works really well with kind of weird shaped data, right? In this case, a smiley face. Right, if we tried to do something like k-means, who knows what we would end up with, right? We'd probably split the circle or the smiley face into like 3 separate groups, the eyes and the mouth, and it probably wouldn't be totally what we're wanting. So these are just some different approaches. Once again, I want to reiterate, do you need to memorize these? No. Do I think that it's important to know that like there are different clustering techniques that work for different data? Yeah, absolutely. That's why we're mentioning it with some pretty pictures. And maybe what are some specific applications? Well, 23andMe, when you turn in your DNA and they tell you where you're from, that a large part is with sequence clustering. So just clustering with sequences, your DNA sequence to be specific. Recommender systems. So, your Spotify daily mix, that is probably based off of some unsupervised clustering method. You can cluster stocks. So, stocks are based in different sectors, meaning, different stocks may work similarly or move in similar ways with respect to one another. And if you're able to cluster them together, you can maybe perform well in that cluster or diversify your portfolio more. And then another one is image segmentation, right? Foreground versus background. When you take a selfie with, we'll say iPhones or Google Pixels have the portrait mode and it blurs the background, right? This is another great approach for that. I think technically nowadays they usually do a supervised approach for that, but who cares? So that was clustering. We'll talk a little bit about anomaly detection. Now, luckily for anomaly detection, it's basically the same. Anomaly detection is usually started with clustering. And so there's a couple approaches. First, just basic statistics. How far away is my sample from the average? We can start with clustering and see essentially how poorly that point is clustered. We can use this thing called fuzzy logic, which instead of just saying, if 1 or 0, you give it a value within 1 or 0. If you're interested in learning more about that, just Google it. And then we can use like fancier statistics like Bayes' rule. But really, just know that unsupervised approaches can be used for anomaly detection, and very often anomaly detection is solved by unsupervised methods. There's a couple reasons for this. One of the most, I'll say, important ones is if you try to take a supervised approach to it, you have maybe a whole lot of normal data and not a whole lot of anomalous data. And so you have this thing called class imbalance, and your model will just try to predict that everything's normal because maybe 99.9% of all of its training points are normal. There's a lot of ways to get around that. Unsupervised is maybe the easiest. Great. So next, maybe let's talk about dimensionality reduction. And this one's, I think, a little bit more exciting and a little bit fun to use. So we have some data set and it has many, many, many features, and we just want to reduce the number of those features, right? There's lots of good reasons to do that, but we'll maybe just talk more about some of the approaches. The first is this thing called PCA, or Principal Component Analysis. Once again, not getting into the math, but what this does is it performs a linear mapping of the higher dimensional data onto a lower dimensional data. And what it tries to do is maximize variance in this lower dimensional space. And so, what does that mean? Whoops. So let's say we have this and we want to turn it from 2 dimensions into 1 dimension. Let me just make sure you all can see the drawings that I'm doing. You can't, because that needs to be there. Okay. So we want to turn this from 2 dimensions, x, y, into 1 dimension. Basically, what you want to do is find some line that's going to go through here that will maximize the variance. And so we'll look at 2 lines. First, we'll say this line, map everything to this line. So draw, just put the point wherever it's closest. And so what do we get here is we get maybe, a single number line. And we get a ton of points maybe in this cluster, right? That's not very high variance. Things are pretty close together. And so let's maybe think of a better way of doing that is what if we draw the line this way? Well, now, again, map the points to the closest point, or closest point on that line. And then when we draw that line, darker colors you all can see, we're going to get a lot higher variance, points maybe more evenly distributed across this line. And that's pretty much it. And sure enough, we can kind of see it at action here. We'll watch the initialization here in a second. And we can see that this line kind of gets swung around to whatever's best, where that variance is maximized. One important detail that I want to mention here is that it is linear. And so, if our data, instead of being, well, linear, is, shaped maybe more like this, we'll just say we have more points like here, like a croissant. It's kind of hard to draw a line through this at some point, right? Maybe that's the best option, but it's by no means perfect, right? Something like this would be much better, but we don't do that. So another one that is very exciting and that we'll look at some examples for is this thing called an autoencoder. And so what an autoencoder does is it learns a compression function and an uncompression function. And what we call these as well is an encoder and a decoder. And really the value here is that in the middle we have this thing called a bottleneck, which has just a smaller value of the data that eventually we hope this decoder can turn back into the original data. And so we'll think for numbers here, right? We have 4, and it gets pulled down into, we'll just say 2 values. We'll say x and y. That's a little hard to read. And then the decoder is going to try to expand that x and y value back to the original shape. And obviously the decoder is going to have to learn what's where. But what we see is that it actually works, relatively well. And we have maybe, some zeros here, maybe a region of 6s. Well, it kind of goes a little bit higher. 2s, 9s, 3s, 8s, 7s, 1s, some 5s. I think that's everything. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, I missed something. Well, there's a number that we missed, but who really cares about 4s? Right? And, I think that this is pretty impressive considering, we've gone from originally these images were 28 by 28, and we turned it into just 2 values, x and y. That's like 99.7% compression for, relatively good reconstructions. And in fact, we can play around with this a little bit. And so we'll graph them out here. And we can see as we just hover over these, we have all of our 8s here, all of our 3s here, our 5s here, 1s, 2s. And, we can even go within this and we'll just move. You see the 1s, maybe they start straight up here and then they get more slanted as we go down there. And so each of these, we'll say clusters, represent some information about it. And so, suddenly we're able to represent this, crazy data set all at once in a really great way. And in fact, we can even see like, hey, look, these 2s are really similar to these 7s, or at least 2s and 7s are somewhat similar. And so let's do a little thought experiment for a second. If instead of having some XY value, it only just classified, and so it gave you basically which group these are in, the best the reconstruction can do, the best the decoder can do, is give you the average of that cluster. And so if it knows it's a 1, it'll give you the average 1, which looks like that. And so as you may be able to imagine, because a lot of that information is lost, when we apply this to maybe more, we'll call advanced data, we lose a lot of that information. And so with faces, you get blurry edges is kind of the what we see, I guess. And then there's 2 newer approaches called tsne and umap. You don't have to know about these. They get a lot crazier in the math side of things. They work really well, is all you need to know. And in fact, that visualization, I cheated a little bit. This uses, I think, umap instead of one of the other ones, instead of autoencoders. So I cheated a little bit there, but you'll have to take my word for it. On now. Great. So we've talked about unsupervised learning. Now let's start to talk about supervised learning. This lecture is probably going to go long. I'm realizing that at this point. I'll try to go faster. So the important detail about supervised learning is that we know the right answer, and we want a model to predict the right answer. And given, another way we can say this is, given our data X, we want to predict the label Y. And there's, major approaches: linear regression, support vector machines, decision trees, and neural networks. But first, I want to talk about kind of 2 important properties. The first is when we do supervised learning, we're doing this thing called function approximation. And what that means is, let's say that we have our sine function here in green, and we are sampling from the sine function. That's all these blue points. But we have some noise, right? Our best possible answer is reconstructing this sine function, but we don't necessarily know that it's a sine function. We don't know what it is. And so, we have a reconstruction, but it's not perfect, right? What we're doing is we're approximating this function. We're approximating whatever transforms our input data into our output data. In this case, our input data is X and our output data is Y, or sine X, I guess might be a better way of doing it. And so we're approximating that sine function. And, the sine function is maybe an easy to visualize simple one, but these functions exist in tons of stuff. It exists in what makes a cat look like a cat. There's a function that, perfectly predicts this is a cat, this is not a cat, based on the image. We don't know it, but I'm sure it's something, because there's a correct answer for each one, right? And so another way you can think about it is for our kind of MNIST data set here of the numbers, you're just trying to predict the correct value for these. And so, here you're trying to predict the number 7. Here you're trying to predict the number 9. And you might be able to imagine this is maybe a little bit more messy of a function. I can't exactly draw it, but you're trying to predict essentially these, we'll say, like Z values, right? And then the second part is this thing that we call overfitting. And when our model overfits, when we train it on our training data, we say that it generalizes poorly. And so what does that mean? If this is our training data and we're trying to say this is a cat, this isn't a cat, and our data has, a white square whenever it's a cat and a black square whenever it's not a cat, well, the model really does not have to look at the cat. It can just look at the square. Right? And so what the issue becomes is, if we then have a new image which does not have a square here, it's not going to have any idea what to do. And so this has generalized poorly, right? Is what we say. It has overfit to the data. And what does this maybe look like from a math perspective? Well, we have this orange function that we're trying to approximate, and we draw this crazy line, right? The blue line being the model. And another way to say this is that is the model would perform poorly on unseen data. And so if we have these green points here, we can see that the errors are huge in this case, extremely huge, much, much larger than essentially the zero error for all of the training points. And so how do we understand if we're overfitting? Well, it kind of comes from this unseen data is we can just take away some of our training points, right? Remove some of these examples and see what our error is as we're training. And we'll look at maybe a more specific visualization of that in the future. But the important thing that I want you to take away is a way to realize if you're overfitting is if your error on unseen data is greater than your error on seen data. So let's talk a little bit about linear regression. We're trying to fit a line to our data. In this situation, one thing that we need to quickly define is what does best fit mean? And this depends on this thing that we referred to before called the loss function. The loss function is really the only thing you need to know about it is you want to quantify how good a solution is, how good your prediction is, right? If we go back, maybe our loss function here is the difference between this point and the actual point, right? For linear regression, one popular loss function is the difference between the actual point and the predicted point squared. The reason why it's squared is just because we like to make bad decisions worse. If it is very wrong, we want it to not be very, very wrong. Being a little wrong is better than being very wrong. And so, in our situation here, what's the line of best fit? Well, we can draw all of our errors and we add them all up and we square them. And, we know that, this is essentially pushing this line this way. These are pushing this line this way. And so we know that it'll move closer to that way as we continue to get better, I guess. Again, with the same side of things, we've been doing regression saying, how do we best fit our data? Well, we can do the same thing with classification and say, how do we best separate our data? And, it's really basically the exact same approach is you take a line and you learn it. In this situation, your loss function is maybe the number of classified points or number of incorrectly classified points. One quick thing I'll mention that I'm not going to get into is we can do this thing called a kernel trick, which is this is clearly not linearly separable. You can't draw a line here that's going to correctly classify those points. Maybe you can draw 4, but you can't draw 1. And so what we do is we just pass it through some function. In this case, something where like the z value is equal to the distance from this point. And suddenly this is linearly separable, right? We can draw kind of a line or a plane right there that separates our data perfectly. We call this the kernel trick. Just the reason I mentioned this is this is really the primary approach in machine learning before neural networks is kernel machines is what we call them. So this is, if you want to go into machine learning, probably something you should at least know the history of a little bit. So I thought it was important to mention. An alternative to linear regression is something we call a support vector machine. Basically, the only thing is with linear regression, these outlier points are sometimes more heavily weighted. And so, what if the real question here is what if we had more green points over here? Well, these are now getting incorrectly classified because of this, essentially. And so what the support vector machine does is it only cares about these closest points here. And it maybe works a little bit better with times when your data is different sizes. So if we have way more, we'll say green points, there's a high likelihood that one of these is an outlier. Or if you just have outliers, it works better. The next thing we'll talk about is decision trees, and I know I'm moving really fast through these. I just want to reiterate, do you need to memorize these? No. Do I want to introduce you to these ideas that, support vector machines maybe, work a little bit better with imbalanced data? Sure. And then if you do have, say, oh, my data is imbalanced, oh, I have a ton of outliers, then you can go and learn more about how this actually works and how you can implement it. So with decision trees, it's actually relatively simple. So you take your data and you try to draw a line through it. And so in this first situation, we'll kind of draw a line straight through the middle. And, there's an algorithm for whatever the best line is. But for now, we'll just say you want to draw a line in a good spot. And then you have another choice, which is either for each of these two sides, either label that side or repeat the split. And so, on this right side case, we can just label this side, gray. And on the left side, we probably want to split again. And so sure enough, we'll perform another split. So we'll go from this, and we'll this left side we'll just label as gray, and then this right side we'll label as gray, and then the left side will perform another split. Same situation here. We can label this as green, and then over here we maybe want to perform another split. So we perform another split, label this as green, label this as, well, obviously I can't label everything G, green, green. I don't have I do have the color gray, 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 right? And, there's some benefits to decision trees. They kind of have this nice pattern of boxes of where things are true and false. So they're kind of nice. And now, the long-awaited topic that I've been trying to hurry towards a little bit is neural networks. I know these are kind of the most popular thing now. And the reason is because they're, I guess, super successful. They're very powerful, is what we'll say. And the way we'll talk about these is we'll first kind of introduce this thing called the neuron. That is kind of the building block of what neural networks are. And so the neuron is this that we're looking at down here. And so we'll break it down. First, we have our input data being, your x values, your, maybe it's height, weight, and age. Maybe it's the color of pixels at a certain location, red, green, blue. It could be anything. Next is weights. These are a little bit like slopes or a little bit like biases, meaning that they're learned, right? This is the thing that we're trying to get better. We multiply each of the weights or each of the input points by that weight, and then we add them all together. And then we have this thing called an activation function, which is optional, frankly, but it adds some nonlinearity, and so it is a very powerful tool. And what do I mean by nonlinearity? Well, if we didn't have an activation function here, if this was, just nothing, what is this, right? Well, x1 w1 plus x2 w2 ... what does this maybe look like? Well, it's just linear regression, right? You have an input and a slope, an input and a slope, and if we want to get fancier here, we can add a bias term, and it's just linear regression, right? If we have two dimensions, we just have x1 plus, well, we won't even call it, wx plus b is literally what we would have if we just had one point. So that's why we have the activation function, is so that we can have some nonlinearity to it. And maybe if our curve is like this, instead of fitting a line that's going to look like this, we can get a little fancier and fit lines that maybe like this, or maybe they're even better. Who knows? Who knows? Okay, so kind of the magical property of neural networks is we can then connect these neurons to one another. And so we start with this input layer here, our data, we multiply it by some weight, we add these things together. This has some output data, and that output data becomes the input data for a new layer. And that becomes the input data for a new layer after that. And so you have this kind of hierarchical pattern to it that has been shown to be very, very powerful. And now let's discuss kind of one of the major properties. Is we said that in the past, linear regression had this thing that we call the closed form solution, meaning there's some formula that you can solve that gives you the best answer. And you're probably familiar with one of these formulas, the quadratic equation, which is some formula you can solve that gives you the roots of a quadratic. And in fact, there's a cubic formula as well, and there's a quartic formula as well. If you knew this, hopefully you don't know this. If you had this, memorized or had to use this at some point, I feel very, very bad for you. But one thing that you may find interesting is there's no solution for quintic for anything, x to the fifth ... There's a formula for some of them, but there's nothing that solves all of them. There's no solution. There's no formula. It does not exist. It's been proven not to exist, in fact. And it's the same thing for neural networks. And so we do this thing, we solve iteratively. And one thing for those of you who are maybe familiar with the term backprop, it can be a little intimidating. It gets into like calculus and partial derivatives. We're not going to talk about that. And in fact, I want to kind of guide you towards the solution without mentioning any math until we absolutely have to. And even then, we're not going to have any fancy symbols or whatnot. So what's our approach? Well, as we kind of mentioned, take a guess and then slightly improve our guess. So let's break this down. Take a guess. Random numbers, right? We have these weights that we're multiplying all of our data by. Random numbers for all of them. Who cares? One thing, just for those of you who are interested in ML, maybe more advanced, initialization does matter. Random numbers is not the best solution. There's a lot of research that goes into it, but that's just kind of a fun fact. But for lack of a better term, we randomly initialize. We'll then improve our guess. And so, what does improving mean, right? We can't just take another random. We can't just take another random guess and see if it's better or worse and go with that one. That hopefully is clear to you that it's not very efficient. Instead, we want to slightly adjust our weights so that we're a little less wrong. And so what we want to know is, how does changing our weights change how wrong we are? And if we take this maybe a step further, we can take the derivative of our loss function with respect to our weights. And so suddenly, we're at math. But really, let's analyze what this is saying. How will changing our weights change how wrong we are? That's all it's saying, is how will changing our weights change how wrong we are? And in fact, how will changing our weights change how wrong you are? And when you do this with large networks, you can really learn very well. And so we'll look at an example here. This is what we call a loss landscape. And so, once again, we've done dimensionality reduction to 2 dimensions. And what we're saying is, if we'll say here, how will changing our weights change how wrong we are? Well, I guess I can't move this. If we change the weights this way, we become much less wrong. If we change the weights this way, we become much more wrong. And what you might notice is that the slope here is, negative. So we can just take that derivative, and that's really it. And in fact, let's even visualize this. And so let's see what's happening. We'll pick a point, and we'll perform gradient descent. Move this down. Start it again. And so we can see our point, slowly moving down there. Maybe I'll speed it up just a little bit. It's just moving downhill each time. But we've hit a little bit of a hiccup, right? We're in this thing that we call a local minimum. And so, maybe an answer is to take bigger steps, in which case, we can eventually get down. If we take, obviously, we'll take 2 big steps, we'll hop right out of the good solution and we'll jump all over the place. No partial derivatives. We are not talking math. But what I want you to notice is, if you take 2 big steps, you don't get to the right answer. If you take, we'll go back to 2 little steps, you don't get to the right answer because you get stuck in these little pits. Local minima is what we call them. So you can see it's just kind of jumping around down there, which obviously is not what we want. And so I want to introduce you to this loss graph here. And so what this is the value of our error, and this is how many updates we've done. And what you might notice is, I guess what you can hopefully tie together is this is your Y value. Whoopsies. Oh gosh, what have I done now? That's your Y value when you're on this, right? And so when we are drawing our line down, we're just recording our Y value, right? Yeah, loss, exactly. So hopefully you can draw the connection between those 2 things, and maybe more advanced takeaway is, why does this keep going down? Well, there's way more than 2 parameters, and so as we're learning, this whole thing is changing as we're learning. Not going to get into that too much. Once again, we're going over time. Just heads up. 5-10 minutes won't be too bad. So, once again, when we talked about overfitting, we said, how do we perform on an unseen test set? Well, if this is your error on the test set and this is your error on the training set, what we can see is, on our seen data, we're doing better. On our unseen data, we're doing worse. And so this is kind of the clear example of what we call overfitting. So kind of staple this in your mind, which is validation or test loss going up, training loss going down, overfitting. right? Meaning, generally for stuff you haven't seen, you're actually getting worse. But for stuff you have seen, you're obviously, you're doing better and better because you're pretty much not ever going to purposefully do worse. Okay, so for the remainder of the lecture, I'll try to move a little bit quickly through these, but I'll probably going to go over. We're going to talk a little bit about different types of neural networks that work well for different tasks. And so we'll talk first about vision and computer vision. So we had our images that were 28 by 28, and we'll just train a neural net to do it. And so we have 784 neurons here, 784 here, 784 here, 784 here, and then we'll just have one output that we'll just say is the value 0 to 10. Well, hopefully you can maybe recognize that this isn't the best solution. We have almost 2 million parameters, meaning it is computationally expensive. It will require a lot of time to train, and for 2 million parameters, you need, rule of thumb, a minimum a million training points. Realistically, you probably want something like 5 or 10 million, and unless you want to draw the number 1 5 million times, you know, you don't want to draw the number 5 or 1 5 million times. And then similarly, we'll ask a question, what if the image is shifted 1 pixel to the left? Your input data totally changes, but, maybe it shouldn't. For example, these two images of a cat are functionally the same. And so some big takeaways is, where the number or where the image is doesn't really matter if it's shifted. And we know there's maybe a hierarchy of what we call visual features. We go from edges to textures, being the texture of a cat, to shapes like an ear, maybe 2 eyes, and eventually objects, being the cat itself, right? Hence, we create this thing called a convolutional neural network. I'm trying to get to the quiz so fast before lecture ends. I'm going to pre-make the quiz. Don't answer. Don't answer it yet. And so what we do is we have this thing called a kernel. I have to do, hold up. Okay. We have this thing called a kernel, and what we do is, we multiply 7 by 1. We put a 7 here. 2 by 0. Put a 0 here. 3, -1, -3. Oh, right. Sorry, I totally messed up. I just was moving too fast. We do 7 times 1 is 7, plus 2 times 0 is 0, 3 times -1 is -3. We add all of those together, dot, 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 and we put that value here. I think this ended up being 6 or something. Yeah. And so this is kind of an important question, and this is your poll question, is which of these image patches will have the greatest value, where white is the value 1 and the black color is the value 0. Which of these will have the greatest thing? And I'll end this when class ends. And again, if you don't want to stay longer, if you're not interested in ML, you can leave at 7:50, of course. But if you are interested, and I encourage you to stay, we're going to be talking about cool stuff near the end, kind of how these visual features create hierarchies. And so, one thing that I want to remind you is, how do we get the value? Well, we multiply, this square by this square, plus this square by this square, et cetera, et cetera. And maybe a more intelligent approach than doing this manually one by one is to just look at some patterns. So we can see here that the left column is 1, the right column is -1, right? And so for this, these are 1s, these are -1s, and they're going to be equal and opposite. And so this entire square is going to give you 0, right? Similarly, maybe for this one, we have 0 here, 0 here, -1 here, -1 here, and so that's going to give us -2. Or sorry, rather this is -1 here as well. I was following the pattern of the previous one. So this gives us -3. Down here, we have 1, 1, 1. These are 0, so it doesn't matter. Gives us 3. Then here, 1, -1, -1, -1, -2. So I'll close the poll at this point. Hopefully you can see. Actually, I'll give just a moment more. Everyone get your answers in. Okay, 5, 4, 3, 2, 1. Poll closed. Okay, poll. Great. So let's see the results. We changed the format of the results. So most people answered either 2 or 3. Hopefully you can see this is B and this is C. Maybe that's where part of this confusion lies. It's okay. It doesn't matter. But so this gives us -3. This gives us 3. What if we created here? Well, one way that we can understand this will give us large values when it is a left edge, and small values when it is a right edge, or negative values even, and 0 when it's not a left or right edge. And so we've created an edge detector. Essentially, when it is large, it says this is an edge, and the same thing occurs here. So we've gone from edges. How do we get textures, shapes, and objects? Well, essentially you do a convolution on the edges, and you say, what are the edges of the edges? And we can actually visualize this in a really exciting way using this kind of trained model. And so we'll go here and we'll visualize some of these. If it will load, please. Rush. Are any of these going to load? Are they all going to be mean to me? So this is a trained model that was trained on some data set. What we're looking at here are essentially these kernels. These kernels. We'll just open one up, I guess. Please load. This is so sad. This was like the coolest part. Please. My heart. Am I on the right thing? Oh, here we go. Okay. And so we can see, all of these have different stuff. And so unit 27, gives us the color yellow, or is large when the color yellow is true. And then we can go further up our model, and we can go to, a layer like all the way up here. And instead of, the color yellow, it's representing this maybe circular or grid pattern that we see on, anything from ladybugs to a leopard to whatever that is, to some sort of sea creature, to a typewriter, right? And then we can go even higher, and we can see maybe more clear, this represents dog faces. And so this is very high when there's a dog face. I like that you think that my mouse drawing is a Wacom tablet. It is my mouse. And so, we suddenly have this really powerful neuron that's representing not an edge, but, a dog face. And so when this is high, we know that there's a dog in the image, ideally. And we can even go higher than this if this page will load, and we can see, all sorts of examples. So this one represents a person wearing a straw hat. This one represents the red wall of a barn, a candlelight, a specific type of bird, a crab leg. All of these may be interesting, crazy things that we're able to do because of the hierarchy here. Okay, I'm definitely going over time, as we can see, so I'm really trying to hurry it up. I apologize for moving so fast, but ML is like my favorite thing, and so I'm getting a little bit excited about it, and yeah, spending too much time. Yeah, I know it does. It does look a little trippy, doesn't it? And so in supervised learning, there's 3 major topics: reinforcement learning, which essentially tries to perform an action that is going to give you the best future state. Basically, the best way you do this is look at all of your actions and then say which of these actions will give me the best reward. And so you build a model to predict the reward based on the action. This is used from everything from self-driving cars, stock trading, medical decision making, and playing games like Go and chess and StarCraft all use machine learning, supervised machine reinforcement learning. There's also natural language processing, where we can do stuff like text summarization, which one of my groups did last semester, who some of them may be your PM. Ask them if they were in group 6 last semester. Text generation, so we can generate stories, translate text, correct your mistakes when you make a typo or even a grammatical mistake, answer questions, right? A small note, if you're interested in NLP, look into this thing called a transformer. It's the CNN of natural language processing. It's actually extremely powerful. So good, in fact, that it's starting to get adopted in a lot of computer vision fields, even though I won't talk too much about it. But if you're interested in NLP or maybe ML research for that matter, shoot me a message and I can teach you about the transformer or something. Yeah, don't just Google the word transformer. You'll get transformers. Maybe transformer ML. There's a YouTuber called Yannick Kilcher that has a great video explaining it, albeit maybe some math heavy. And then we can talk about computer vision, which we looked at a little bit. Semantic segmentation, saying, for my webcam right now, you can see there's a background and there's a person, right? Labeling each pixel as background or person is semantic segmentation. Image classification. Classify my webcam as a picture of a human. Object detection. There's a human here, right? Or maybe two or 10 or 100 humans, or here's a pen, right? Image generation is really interesting and cool, and albeit sometimes difficult. But I encourage you, if you're interested in kind of generating art with machine learning, image generation is a very cool topic. Pose recognition, how is someone standing? What actions are they making? Stuff like that. Okay. Once again, apologies for going over time. I just get really excited about this stuff, so I put a lot of effort into this lecture. I hope you all had as great of a time as I did. If you are interested in learning more, feel free to shoot me a message. I'm happy to kind of discuss this with you all. The big stuff I want you to take away is that this is a powerful tool, and it's a tool that you can have easily in your tool belt. And the only thing you really need to know at this stage is that you can do these things with it. If you want to do text summarization, there's a way to do it. If you want to do object detection or, self-driving cars, there's a way to do it. There's an approach. And as long as you know that these things exist, I'm happy. If you then want to go and start to learn about how to do it or do a project in it, well, projects is kind of the whole purpose of this class, right? Um, awesome, right? Awesome. Take it and learn about the application and the content. But nonetheless, I think that machine learning or even just data analytics should be a tool in everybody's tool belt, every developer's tool belt in our current age. I mean, it's so powerful. Even if you aren't going to spend infinite time on it, it's just a powerful tool. Okay. Sorry for going over time. Overall, I only went 6 minutes over, so it's not that bad, right? But I did also go crazy fast, so apologies there. If you all have any questions, talk a little bit in the Discord. Again, I'm like so happy to talk more about ML. I'll even hang out in voice a little bit afterwards. But thank you all. We are starting Rust next week, and so that is basically going to be the topics for the rest of the semester. And so you'll get to learn a lower level language like Rust, which some of you may love, some of you may hate. I love it, and so. It's also, I think, most importantly, something cool and something valuable to learn. Rust, just as a fun fact, is the most loved programming language by those who use it. So maybe, you'll become one who loves it the most as well. In any case, I'll see you all next Tuesday, or rather, Matt will see you next Tuesday. Thank you all, and bye-bye.